In the previous video, we learned about type class. We looked into type class syntax in a couple of different languages. We also talked about limitations of implementing type classes in TypeScript and talked briefly about FPTS implementation of higher-kinded types to overcome these limitations. In this video, we will look into how to use tools in FPTS library to define type classes. Alright, we need to do some groundwork for setting up our structures like option, list, and either in FPTS so we can benefit from FPTS higher-kinded type implementation. To save time, I've already installed FPTS as a dependency to this project, but let me know if you want me to create a separate video on this. Alright, in order to set up our structures like option, list, and either, we need to add code to HKT module inside FPTS library package. In order to do that, we're going to use a feature called module-augmentation inside TypeScript. So the module that we want to add code to it is inside FPTS library, and the module is called HKT, short for higher-kinded type. Inside this module, there are a couple of interfaces called URI to kind, followed by some number. So we have URI to kind 2 and so on. Based on how many number of type parameters our type constructors and structures receive, we're going to add them to the corresponding URI to kind. For example, list receives one type parameter, so we're going to add it inside URI to kind. List A. And URI to kind receives one type parameter A. And our example is option, so we're going to add it here. Either receives two type parameters, so we can add it here. E and A, and this is also a generic interface. Let's import all the stuff that we need. And by the way, I have a dedicated video for each of these structures, so if any of these looks new to you, please check out my video on each of them. So we have list has cons, nil, match, and we'll rename it to list match. Let's import the stuff for option. Option, sum, none, match, and let's rename this to option match. Let's import stuff for either. So we have either, right, left, match as either match. Something that may be confusing here is that how does this work? Are we overriding URI to kind interface inside HKT module? Let me explain this by an example. Let's have a person interface with a property inside it called, for example, first name. Let's define another interface with the same name and add last name to it. If I create an instance of our person, let's call it John. What do you think John expects in between the curly braces? Let's do autocomplete. It expects both first name and last name. So first name, John, and last name, for example, Doe. The way TypeScript works is that if you have multiple interfaces with the same name, the properties underneath those interfaces are going to get merged. So FPTS is using multiple features in TypeScript to make higher-kinded types possible. First, it uses module augmentation to add code to a module inside the FPTS library. Then it is going to rely on this feature of interfaces to let developers dynamically add their structures to URI to kind interfaces. This way, developers can dynamically add their own structures and type constructors to FPTS. Let's clean this up a little bit. Alright, now that we're set up our structures in FPTS, let's try to define type classes. We've already seen how to define type classes for concrete types like magma, semigroup, monoid, and group in previous videos. But when we tried to come up with a single definition for functor, we got into some challenges. If you remember, we couldn't pass type constructors as type parameters when we were trying to instantiate our interfaces. Let's first review functor symbolically. Functor has a map method, which is a generic method. It first receives a function from A to B. It then receives FA and returns FB. Well, this is not a valid TypeScript syntax. One way we can overcome this challenge is by using higher-kinded type implementation in FPTS. So let's fix that, HKT FA, and we can say HKT FB. Now we need to import the HKT from FPTS, so we can say HKT, and it is coming from HKT module. Now what we have here is a single definition of a functor in TypeScript. Pretty cool, right? But unfortunately, we are not done yet. We need to write some boilerplate code in FPTS for our type classes. For each kind and arity of type constructors and structures, we need to define an interface. For example, for type constructors with one type parameter, like option and list, we define an interface called Functor1. For structures with two type parameters, like either, we define Functor2. And so on. Functor1 has the same definition, but for kinds that have exactly one type parameter. So again, we're going to have map with two generic types. It receives a function from A to B. It then receives FA of exactly kind that receives only one type parameter to kinds F and B. Same for Functor2. It has a map method, but with three type parameters. It receives a function from A to B. It then receives FA of kind that exactly receives two type parameters, E and A, and returns kind 2, F, E, and B. We can also limit our F type parameters to exactly the kind of type constructors they expect. We do that by adding extends from URIS. Now F in Functor1 can only be of type URIS, which is a union of structure names from URI to kind, or in simple words, union of keys on URI to kind interface, which here is list or option. Same for Functor2. We specify F can only be of type URIS2, which here is either. Let's import all of these missing types from FPTS. So we have kind, we have URIS, and we have kind2 and URIS2. There is one more thing we need to add for FPTS type classes. We need to add URI property to our type class interfaces, which holds the name of the structure that we are defining instance of type classes for. So let me make a little bit of a space here. And let's add these URI properties. Now that we're done with our Functor type class definition, let's create type class instances for our structures. Let's start with option. We have already seen how option functor behaves and implemented in the previous videos, but let's go through it really quick again. Let's create more space here. All right, option receives one type parameter. So we're going to implement functor1, and for its type parameter, we're going to specify option. URI would be option. And the map function looks like this. It first receives function f, then we're going to pattern match over our input. If it's none, we're going to return none. If it's sum, we're going to extract the value out of it, call f on that value, and wrap it in sum again. And this is the type class instance for option functor. I'm going to leave list as an exercise to you. Let's move on to either. All right, let's create a little bit more space here. Let's implement type class instance for either. So since either receives two type parameters, we need to implement functor2. And the type parameter is either. URI is again either. And the map function looks like this. It first receives a function f, and then we're going to pattern match over the input. If we see an error, we're going to extract the error and simply wrap it in left again. If we see right, we're going to extract the value inside it. First call f on a, and wrap it in right again. Okay, now that we have our functor type class and couple of functor type class instances, we can write functions that abstract and work on any functor structures compared to before that we needed to define separate functions for the same logic for option, list, and either. Let's define a lift function, which works pretty similar to the map method, but in a function form. So lift is a generic function with type parameter f. The function expects f to be a functor, so we pass functor type class instance to it. It then receives a function from a to b. So a to b. And this is generic, so let's add those type parameters. It leaves this function and return a new function that first receives fa of any structure of kind unary or above, meaning hkt, f, and a. Transform the type inside the structure using f and returns hkt of f and b. So the implementation of the lift looks like this. It returns a function that first receives f, then fa, then it's going to call map method on f and fa. If you are confused why f.map receives two parameters, it's because we implemented our map methods point-free style. We could have said fa and call this function with fa as well. Since fa is the same on both sides, we can cancel them and have a simpler implementation. I've already covered point-free style in the previous video, so if this looks new to you, please check out my previous videos. Well, we are not done with our lift function yet. We have some boilerplate code to write. Let's do that. We need to overload our lift function so it works with different kinds of structures. So let's do that. I'm going to copy the previous line and I'm going to remove this. And then I'm going to do the same now each time for a specific kind. For example, this one is going to be for a kind for a functor 1. And I'm going to change these HKTs to a specific kind here. So this one for kind, and this one for kind. This means that we want this overload specifically for type constructors and structures that receives only one type parameter. And we need to do something else here. We need to specify and limit that our f is only of type URIS, meaning only the type constructors and structures that receives only one type parameter. We are going to do the same for structures and type constructors that receives two type parameters. So let's copy this line and do the changes. That is going to be URIS2, changes to functor2. We have an extra type parameter, e. The function is going to stay the same. fa would be kind2, and this is going to be fena. And let's move forward. Kind2 again, f, e, and b. We need to do the same for structures and type constructors with more than two type parameters as well. So we should have functor3, functor4, but for now, let's say this is good enough. Now we have a lift function that works with any structure that is a functor, regardless of the number of type parameters it receives. Let's make some space here. Let's try this with our good old increment function. So increments is receiving a number and returning a number. Constant increments of type increment. It receives a number and returns 1 unit above it. Let's try this for option. Let's define lift increment function. We're going to call lift with option functor, and we're going to lift increment. If I try this, lift increment, let's try this with sum of 12. If I save, we get sum of 13 on the right. And if I try this with none and save, we get none on the right. Next, let's try this with either. Lift increment 2, lift this time either functor, and again let's lift increment. Let's try this with right of 12. If I save, we get right of 13 on the right. And if I try this with lift increment to, if we try this with left of, for example, error, if I save, we get left of error on the right side. As an exercise, try to understand what code you need to add to make the lift function to be able to work with lists as well. Okay, here's a question. Do we need to write all these overloads every time we want to create a function that receives a functor? Unfortunately, yes. At least for the HKT implementation of FPTS. There is a newer and seemingly better implementation of higher-kinded types in FPTS that probably needs less boilerplate code. But here's the thing. My intention here is to teach functional programming to many people who, like myself, are coming from the web development background. As we know, JavaScript is a dominant language in the web development, and TypeScript brought type safety simply by decorating JavaScript. Is TypeScript the best language to code functionally? Probably it's not. At least right now. But it's possible to code functionally with it. In almost any decent-sized company, you can find a JavaScript project. But can you say the same for Haskell or PureScript? So why should we learn a whole new language like Haskell just for studying something which we can learn right now with a familiar language like TypeScript and use the techniques in our day-to-day coding? So bear with me on this, and I promise you, if you ever decided to pursue this further by learning functional languages like Haskell, the migration would be super smooth because concepts are the same. It's just the syntax in those languages would be more intuitive to design and coding functionally. And with that, thank you for watching this video. Please like and subscribe, and I will see you in the next one.